Hi everyone, and welcome back to physics. This is Mrs. Hutchinson again, and we're going to continue our discussion with tools of physics, but now we're going to get into yet another aspect of measurement that should really be a review, so scientific notation. So let's get right to it. So scientific notation, as you probably can recall, since you've been doing it since, I don't know, 5th, 6th grade, maybe, even if not earlier. Scientific notation is used to express either very small or very large numbers. So a prime example would be, 3,560,000,000 meters, because that's got a lot of zeros. What we like to do is we like to express it in terms of scientific notation. So what we do is we make that number here out of a power of 10. Or if we have a very small number, like a number right here, 0.000000492 seconds, so a very short amount of time, or a very small number here, we like to express that in scientific notation as well. Now, to convert into scientific notation, here's what you do. Just a refresher. If the number does not have a decimal place or a decimal point, put 1 after the last digit. Then move the decimal point 1 digit at a time, counting the digits until there's 1 digit to the left of the decimal. In other words, you want a value between 1 and 10, but not 10. Okay, so 9.9 or something like that. Then you'll report the number as digit with a decimal and digit times 10 to the n, where n is the number of digits moved. So for large numbers, you will have a positive exponent, and for small numbers, you will have a negative exponent. So let's do some examples on the next slide. So let's convert the following into scientific notation. Here we have quite a large number of 275 million miles. So there's a large number. That decimal is not present, so we're going to place it at the end here. We're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, so that we now have 2.75 times 10 to the 8th miles. Again, our exponent is positive because we have a number that is larger than 0 that we're dealing with. Next one, we've got 44,000 kilograms. So again, our decimal is missing, so we'll place 1 at the end of the number. We move it 1, 2, 3, 4, so we get 4.4 times 10 to the 4th kilograms. Let's go over to the next one. We're dealing with a very small, itty-bitty little number. So our decimal is present, but what we want to do is we want to make sure that we still have a digit to the left, a non-zero digit to the left of our decimal. So let's move our decimal place over until we get that. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, holy cannoli. So 3.79 times 10 to the negative 11 seconds. We have a negative exponent because the number that we're dealing with is much smaller than 1. And then last but not least, we've got 9.83 centimeters, or that's silly, 0.983 centimeters. So we'll take our decimal, we'll move it 1 place over, so we get 9.83 times 10 to the negative 1 centimeters. You'll notice with all of these measurements that all of our numbers have just 1 number to the left of the decimal. That's what you're looking for when you're trying to create scientific notation. Again, this should be a review. Let's go on to our calculations. You will want your calculator out for this. So if you don't have your calculator out, please pause the video and get your calculator out. So now, with our graphing calculators, or with our scientific calculators, the TI-83 doesn't really do order of operations, neither do our scientific calculators. The TI-89s do order of operations, so if you're using one of those, you really don't necessarily need parentheses. It will follow all of the rules that you will need. However, I wouldn't recommend using a TI-89 because you can't use that on the Regents. So again, you want to practice with what you're going to have to eventually use. So let's take a look here. We've got 2.45 times 10 to the negative 12 and 7.543 times 10 to the 10th. You'll want to put both of those into parentheses. So parentheses around the outside of 2.45 times 10 to the negative 12 times, and then start another parentheses, 7.543 times 10 to the 10th. And when you hit enter, your calculator should spit out a number close to 1.85 times 10 to the negative 1. Sorry about that, pardon me. Let's take a look at the next one. Again, it's multiplication, so we've got 8.83 times 10 to the 34, so you want to put that into parentheses, times 3.29 times 10 to the negative 10th. Again, keeping our scientific notation values in parentheses will help our calculators figure out what we intend to multiply or what operation we intend to do first. Okay, so you plug that into your calculator, and your calculator should give you 2.91 times 10 to the 25th. If we go over to the next one, we've got division. So this is really where our parentheses is very, very, very important, because we've got multiplication and division, so two different operations. So we've got 6.34 times 10 to the 22nd divided by 5.22 times 10 to the negative 4th. So you want to put parentheses around each of those scientific notation numbers, and you should come out with 1.21 times 10 to the 26th. Last but not least, this one's a little tricky, so again, you're going to want a lot of parentheses here. You're going to want parentheses around each set of scientific notation numbers. But then, because we are separated by addition, we want parentheses around each division. Okay? So the way that you start this in your calculator is you'll have parentheses, 6.237 times 10 to the 12th, close parentheses, divided by parentheses 8.56 times 10 to the 36, close parentheses, close your first set of parentheses, plus, and now you start again, double set of parentheses, 4.294 times 10 to the 15th, close parentheses, divided, open another parentheses, 5.894 times 10 to the 38, and you'll close both sets of parentheses, hit equals, and it should come out with 8.01 times 10 to the negative 24th. Okay, so you got a lot of parentheses going on there. If you struggled to get any of these answers or anything close to these answers, check with someone next to you, see what you're doing wrong when you're plugging these into your calculator. It's not so much that you don't understand what's going on, it's just a matter of getting it correct in your calculator. Okay, so let's move on to the next part. If you do not have your reference tables out, please make sure that you pause the video and you get your reference tables out. You're going to need to flip to this reference table. Of course, I'm pretty sure it's right on the front, but make sure that you get your reference tables out. We can write on your reference tables, however, the ones that you'll use for a test or a quiz will not have whatever you wrote on it. They'll be blank. And by blank, I mean just the tables, no handwritten information. So, if you remember from chemistry, we had a reference table that we used to get us from one metric unit to another metric unit. Well, we have a similar kind of table in physics. And that's what this table is telling us. So let's figure out how to read this, how to create a conversion factor using this particular reference table. Why? Because physics, you do a lot of math and you will wind up doing a lot of conversions. So it's good to get to know how this particular reference table is set up. So pretty simple. What we're going to do is you'll always place a 1 in front of the prefix. So let's just say we want to deal with picograms. We want to convert from picograms to grams. So we place a 1 in front of the unit that has the prefix with it. So a 1 goes in front there. We'll place our base unit after that, which is grams, then do an equal sign, or 1 picogram I should say, is equal to the factor, so 10 to the negative 12, followed by the base unit itself. Okay, so we place a 1 in front of the prefix, we place the base unit after the prefix, we've got an equal sign, and we place the base unit again after the notation. Now, you could write it the way that we just wrote it, or you could actually change the notation and you could write 1 gram equals 10 to the positive 12 picograms. So you could get it directly off of the reference table itself, or you notice what we did here was we just flipped it. We now have 1 gram, so we took our base unit and placed a 1 in front of our base unit, and in order to do that, to get what our prefixed unit is equal to, we just took the notation and made it positive, or the opposite value. Either way, whatever you would like to do works. Just know that you have to be able to create conversion factors and utilize them. Okay, so let's move on to some practice here. So let's consider the following examples. Let's illustrate what these metric units are. So in each line from the above table, we can use each line to produce 2 different equalities. In other words, here's our example. 1 meter is equal to 100 centimeters, or 1 centimeter is equal to 0.01 meters. Now again, what that means is 1 meter is equal to 10 to the second centimeters, or 1 centimeter is equal to 10 to the negative second meters. So what we did was we had this conversion factor here. The second one, this one, we placed a 1 in front of the prefix, and we set it equal to our base unit. For the first one, what we did was we flipped it. We had our base unit had the 1 in front, which meant since our base unit has the 1 in front, we had to take the exponent and actually make it positive. It is up to you which one you would like to do and which one you prefer. It doesn't matter to me. So let's take a look at these next ones here. So we've got kilograms. So let's convert. So 1 kilogram. If we take a look, here we go. So we notice that the 1 is in front of the kilo. So that means that we just simply set it equal to our factor of 10 to the third. The next one, we notice that the 1 is in front of the base unit, which means that we now have to flip our exponent and make it negative. 1 hertz is equal to how many megahertz? Well, let's erase this and we'll get to, so mega is right here. We notice that the 1 is in front of the base unit, so that means that we actually have to make our factor the opposite of what it is showing in the table. So we've got 10 to the negative 6 hertz. Or we could say that 1 megahertz is equal to 10 to the 6th hertz. Let's do the next one. If you're getting really comfortable with this, go right ahead and complete the next couple ones on your own. I will catch up with you. Okay, next one, we've got 1 liter equals how many milliliters? So again, we're starting with our base unit of liter. So since we're starting with our 1 in front of our base unit, we have to change the exponent. So it's 10 to the 3rd milliliters, or 1 milliliter equals 10 to the negative 3rd liters. Last but not least, we're talking about nanoseconds and seconds. So we've got our 1 in front of our seconds. So our 1 is in front of our base unit. So that means that we have to change our factor. So we've got 1 second equals 10 to the negative 9th nanoseconds, or 1 nanosecond is equal to 10 to the negative 9th. I'm sorry, I misspoke before. 1 second equals 10 to the 9th nanoseconds, or 1 nanosecond equals 10 to the negative 9th seconds. Okay, so that's how you would use this particular reference table to help you convert from one unit to another. Again, that should be a review from chemistry. The only thing that I would say that's kind of new for physics would be estimating measurements. So, the ability to make reasonable estimates of the size of things is actually something that's really important, and it's really hard to teach because it's based on you and your past experiences and what you can relate those sizes to. So let's just take a prime example. I'm pretty sure you all have been driving on the highway and someone's coming up really fast. You're going, say, 72 and a 65, which is fairly acceptable unless, of course, your parents are cops, in which case you go 65. But you're going 72 and a 65, someone's coming up really fast, you slide over to the right lane and they blow by you. You can tell that they're going much faster than the speed limit. That's based on your experiences. So this is what I mean. If you were traveling in a car with someone driving 100 miles per hour, which you do not ever do, I know I'm not your parents, but please don't do that. It doesn't leave you much room for error. So please don't ever go 100 miles per hour. But if you were in that vehicle going 100 miles per hour, you would probably be able to estimate that the speed that you were going is much greater than the speed limit, even without looking at the speedometer. Why? Because you would notice the trees are actually a blur. Okay. Now, a tool that is commonly used for estimating is called order of magnitude. You have dealt with order of magnitude, but you probably don't even know that you've dealt with order of magnitude. When you describe the order of magnitude of something, all you're talking about is the exponent of the factor of 10, when that number is written in scientific notation. So, here's our example. If we have a truck, a little truck, maybe it's a decent sized truck, it's 400 centimeters long. 400 centimeters is equal to 4.00 times 10 to the second centimeters. So the order of magnitude would be either 10 to the second or 2. Either one. So order of magnitude is simply the factor that you're multiplying by. A pencil is 8.2 centimeters long, so we would write it as 8.2 times 10 to the 0. So the order of magnitude is 10 to the 0, or of course, 0 itself. That's probably the only difference for you for physics as opposed to chemistry. So, now that we've discussed that, let's get on to our guided practice. Yay, woohoo, yay, let's practice. So, scientific notation, pretty simple. Let's get to these. Let's get to them really quickly. So 123 billion, that would be really nice if that were in like dollars. I would even take pennies. So 123 billion, we've got no decimal there, so let's put it right here at the end. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1.23 times 10 to the 11th. Beautiful. So again, remember our exponent is positive because our number is gigantic. Actually, it's much greater than 1. Taking a look at the next one, we have itty bitty little number. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3.234 times 10 to the negative 9th. Remember, our exponent is negative because our number is much, much, much smaller than 1. Next one, I would even take $46,500,000. Like, I'm not really super picky, so it doesn't have to be 123 billion. It could 46.5 million is fine. I would settle, not a problem. So we don't have a decimal. We've got our decimal, place it at the end, and we've got 3, 6, 7. So 4.65 times 10 to the 7th. Okay, pretty simple, pretty straightforward, pretty much a review, one would hope. What I want you to do now, pause the video, try questions 4 through 6. Then I'm going to go through the answers once you're done. Hopefully you've paused the video so that you can try these scientific notation questions on your own. You're only hurting yourself if you're not doing that, so please make sure that you are doing that. So 834,000, 1, 2, 3, 4, 5, 8.34 times 10 to the 5th. Yay! 42,700. That's a number. 42,700. 1, 2, 3, 4. 4.27 times 10 to the 4th. Yay! We are just a cruising. Last but not least, 1, 2. 2.832 times 10 to the negative 2. Who knew? Okay. If you got any of those wrong, make sure that you pause the video or you go back and you see what you may have been confused on. If you got them all right, let's move on, people. Let's do this. Next, we're going to convert into standard notation. Pretty simple, pretty straightforward. What we're going to do is we're going to take our decimal, and since this order of magnitude is positive, that means our number has to be larger than 1. Bam. So we're going to move decimal to the right. So we would have our decimal of 6.23. Let's move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Holy cannoli. So we've got, oh, wow, that's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Bam, bam, bam. I mean, I would take that in pennies. That's fine. That's a large number. I wouldn't even, I would take that in pennies. That's fine. Not picky. I don't even need dollars for that value. The 623 trillion? That's fine. Next one, since our order of magnitude is -8, we're going to move the decimal to the left because our number is going to be less than 1. So we've got 9.2367. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Oh, I just barely. I had to squeeze that one in. So 0.123. And there is our value. Now that number I don't need in cash. That's fine. Next one, order of magnitude is positive. We're going to have a number that's larger than 1. So 1, 2, 3. So we get 6540. Bam. All right. So see, we're geniuses over here. Next, because we're brilliant, try the questions 4 through 6 on your own. So pause the video, try them on your own. I'm sure you're going to cruise right through them. That's what I'm going to do when I show you the answers. Go right ahead and pause the video. Hopefully you paused the video. So here we've got our answers. We've got 0.007342. Next is 332. 1, 2, 3, 4. Bam. Okay. And last but not least is 0.8432. I just showed you the answers here because this should really be a review. If you didn't get any of those answers, or if you got a couple wrong, make sure that you pause the video and go back and double check. So now, estimates, because we all love to estimate things. So this is where it gets really, really tricky for some people. So you want to use your unit of conversions, your reference table unit conversions, to help you if you need to. So let's take a look. I'm going to help you with the first three, and then I want you to do questions 4 through 6 on your own. The length of a human finger. Now, they don't tell you which finger, but just think about it logically. Whoa, that was silly. So 10 to the first centimeters means that we're actually talking about 10 centimeters. 10 to the second centimeters means that we're talking about 100 centimeters, which is actually a meter. 10 to the negative second centimeters means we're talking about 0.01 centimeters, so actually 0.1 millimeters. And 10 to the negative third is this, so actually 0.01 millimeters. So that's pretty tiny. So looking at your fingers, which one seems the most logical? Well, 0.1 millimeters and 0.01 millimeters, that's like a sheet of paper. So it can't be those. And I don't know about you, unless you're an absolute giant, your fingers are actually a meter long. Can't possibly be that. So the only logical answer would be around 10 centimeters. The volume of our locker. Let's take a look. All right. Well, we don't have the ability to go take the volume of our locker, so we're going to have to guesstimate. So 10 to the negative 1 liters is 0.1 liters. 10 to the 0 liters is, well, 1 liter. And then we've got 10 liters, and we've got 100 liters. So let's think about this. Your locker is fairly big. A liter is actually just 2 water bottles. Let's take what we know, 2 regular water bottles. So your locker is bigger than 0.1 liters and definitely bigger than a liter. Now, is it close to 10 liters, which would be 20 water bottles? Or is it close to 200 water bottles? I'm going to go with it's probably closer to 20 water bottles. So again, this is where you have to take stuff that you know and reference and help you. The Regents exam absolutely loves these kinds of questions. The height of a tree. Is it a sapling? Is it a redwood? We have no idea. So let's try and figure out the most logical option for us. 10 to the negative 2 meters. Well, okay. So that's 0.01 meters. Okay, that's itty. That's like a centimeter, isn't it? Okay. 10 to the 0 meters is, well, 1 meter. Then we have 10 meters, and then we have 100 meters. 100 meters is about 300 feet-ish, just for rough guesstimation. It's definitely not A. Most trees, when they're full grown, are more than a meter. Most of them are not 300 feet tall. So our best answer would be C. So what I want you to do is take your knowledge and apply them and try the next question. So pause the video, try questions 4 through 6. So let's continue with this. The mass of a high school football player. Okay, just for your reference, 1 kilogram is equal to 2.2 pounds. So we've got 1 kilogram here, 10 kilograms here, 100 kilograms here, and 1,000 kilograms here. So to put that into pounds, 2.2 pounds, 22 pounds, so unless you're like a toddler, 220 pounds, that's a pretty hefty linebacker, but you never know. And then 2,200 pounds. Probably our best option is C. It's a pretty big boy, but the other ones just don't simply make any sense. Let's see, the following, which of the following is the approximate thickness of a sheet of paper? So we've got 1 centimeter, 0.1 centimeters, 0.01, 0.001 centimeters. All right, so this one's definitely tricky, but it's about 100 sheets of paper per 1 centimeter. So C actually makes the most sense. That one's a little tricky. Your height. And people are like, well, I'm way different height from the person sitting next to me. I understand, but let's try and figure out what our best option would be. 10 to the negative 1 is 0.1. Then we have 1 meter, 10 meters, and 100 meters. Okay, so 0.1 meters is actually 10 centimeters. So pretty sure you're not anywhere near close to 10 centimeters. 1 meter, it's about 3 feet. So let's see, we'll get there. It's about 3 feet. And then we've got 10 to the first, so 10 meters is like 30 feet. And then we've got 300 feet. Best option is we're all pretty close to 3 feet. Okay, not exactly ideal, but you got to get pretty good at estimating here. So now, what I want you to do is work on the guided practice for scientific notation. And once you are done with that, I'll see you with our next video.